In my job, I'm doing security audits, usually for web applications. And sadly, oftentimes I don't get the source code and need to test the web application blindly as a black box. But you can still get a lot of hints from the backend implementation, for example, through error messages, stack traces, unique HTTP headers, or simply how the API endpoints behave and feel like. For example, when you have a Go backend, but you don't know that, and it's using the popular gjson library, then the incoming JSON request can have an equal sign at the end. This library will happily parse it, while the built-in JSON library will throw an error. Sometimes I test for things like this in order to figure out if maybe the backend is using Go. This kind of knowledge, I think, is very helpful because every programming language and every framework has its own typical issues and pitfalls. So when you know the backend, you can optimize your testing. You can look specifically for issues in that direction that is common in that world. And of course, this applies even more once you get access to the source code and you have full white box test and you can see the whole logic and you see exactly the libraries and frameworks being used. And at this point, it's very, very helpful when you can obviously read that code and you are aware of typical pitfalls and programmer mistakes to look out for. So let's talk about such a pitfall in Go code that I was not aware of. This video is sponsored by HEXTREE.io, our online training platform, but more on that later. Let's get back to the video. At the 38C3, HXP, so that's the CTF team primarily from the Technical University of Munich, they organized the Congress CTF, and our team Alles didn't really play, but some of us joined forces with Fluxfingers to help them. And one of the challenges that I looked at a little bit was the challenge Fajny, Jagazyn, Wartości, Kluczy. Sorry, I had to use AI to pronounce that for me. This was a Go web challenge, and according to ChatGPT, this roughly translates to key value store. And that is exactly what it was. So let's get a quick overview of the challenge and see what it is about. In this challenge, we get access to the source code. And when you unpack the files, you can find the following. There are two Go files, KV and frontend, and Docker files so that you can quickly run it locally. In the Docker file, we can also see that the flag.txt is copied into /home/ctf. So our goal will be to leak the content of the flag from here. The Docker file also has a lot of weird additional code, which you might think could have something to do with the challenge, but somebody from Fluxfingers told me that this is likely just code to harden the challenge container, clean it up a bit. At the end, you can then see that it executes the frontend binary, which was compiled up here. So the frontend is our entry point. With the Docker compose file, we can also easily run this code with Docker locally. The challenge is running now on local port 8080, and when we then open this page in the browser, we can see the message, "We booted a fresh web scale key value store just for you." If we look into the front-end Go code, we can see the message here. So this is handling an incoming HTTP request, and this message only appears if we have no cookie with a valid session set. If we have a session, then the request is actually passed into this HTTP proxy handler. So something else is then actually handling the request. If we look around a bit more, we can also see that the frontend executes the KV binary, and then it creates this HTTP proxy with a Unix domain socket called KV socket. And if we look now into the KV program, we can see that it listens on this KV socket, and it also declares two HTTP handler functions, set and get. So it looks like HTTP requests incoming into the frontend get forwarded here via a Unix domain socket to the KV process. We can also see that if we try that out in the browser. If we have a session, we can call set with the name, for example test, and a value. A short one will fail with a 502, that's because of a bug in the code, but a long value will work. And now that we have set this value, we can now get the value with a call to /get. Surprise, we can set and get values. It's a key value store. Now, this feels weird, right? Why use this front-end code that executes another Go binary and then using Unix sockets to forward incoming requests to the backend KV process? If you know how typical web applications are set up, this is very odd and uncommon and suspicious. And this could have two reasons. Maybe it's necessary for the CTF challenge in order to do user separation. Or this is part of the vulnerability. Maybe there's an issue with the exec or an issue with the Unix socket. If we look closer at the code, if we don't have a session, we can see that the session ID for the cookie is returned by new KV. And in new KV, the KV binary is executed and a proxy is set up with a unique Unix domain socket connection file. So this means for each new session, the frontend creates a new backend process. And given then the session ID in the cookie, it can get the correct proxy backend and route the HTTP requests to the correct KV process by going through the Unix domain socket file. Okay, this makes it a lot more likely that it's just a setup to do user or team separation for the CTF, but you can never be sure. And it really confused me a lot, to the point where I was not focusing on the right path, and I missed it completely. Because eventually somebody from FluxFingers noticed something very obvious. There is an arbitrary file read. You provide the name or the key that you want to read, it's passed to OS open, it opens that file, and then it reads that content and returns it. And if we try that, that's how it works. We can read etc passwd. So can we now just read the flag.txt file? Unfortunately, that does not work. There's this check path function, and it checks that the file path does not contain a dot and does not contain the string flag. So flag.txt fails both checks. Of course, there were ideas if we can somehow get a symlink to the flag, or we could use the set function, because obviously there's an arbitrary file write as well. The name and value is just used to write file. And very suspicious that threw us for a loop was these permissions, 777. The file gets execution permissions. So could we write a binary or script or overwrite something and then abuse the exec from the front end or something else to get RCE? But none of those ideas really led to anything. Until someone had a somewhat obvious idea, the proc file system. It contains information about every running process, including the file descriptors opened by other processes. And those are symlinks to the actual files. So what if another process has the flag opened? Then we could bypass the check path function. There won't be a dot and no flag string in the file name. But there doesn't seem to be other processes that open the file, right? Nothing in this code reads and opens the flag file, unless other teams solve the challenge. Because if another team somehow opens and reads the flag with their process, we can get the flag through the file descriptor symlink to the flag.txt file. This is of course not the intended solution. This was clear to us as well. And FluxFingers even asked the organizers if it's okay to do that, because it could go against the rule of not attacking the infrastructure. But they said it's fine, so we did that. Here's the code for it. It also uses one more trick to optimize this. You need to know the process IDs of other processes, and you could of course guess them, but you need to be fast when a new process is started, otherwise it might quit again and the file descriptor is gone. But you can use another useful proc file for that, and that is located in proc sys kernel namespace last process ID. This file gives you the last allocated process ID inside your namespace, and so you can use this with the arbitrary file leak to check if a new process got started, and if yes, you can then use that process ID to leak the file descriptors, and maybe that one opened the flag. So this script was running, and now we just had to wait, but it didn't take too long and we got the flag. And most likely it was not even another team solving it, because in fancy modern CTF setups you often have health checks for the CTF challenge services. Oftentimes they are running the solution script against it. This way that you can always confirm that the challenge is still working as intended. So probably their flag checker solved the challenge to confirm it's working, and we leaked the flag from that. But what was the intended way? That's actually the whole point of this video, right? In the end, only 8 teams solved it, even though the challenge difficulty was estimated by the organizers to be easy. Well, after the CTF, I was very curious and waited in the Discord server for the CTF for the intended solution, and it turns out the vulnerability was right here. Do you see it? Obviously, I didn't see it either. It has to do with the differences of :equal and equal. :equal means declaration and assignment of a value, while equal is just an assignment. And this is important. Go has built-in concurrency features. That makes Go pretty unique and powerful. Concurrency is everywhere in Go, and so you need to be careful with thread-safe code and variables. Let's have a closer look at this code. Of course, these HTTP request handlers can run concurrently. Multiple requests in parallel can be handled here. So there can be multiple requests with get or set calls in parallel. Now look here. Do you see how this error variable is only assigned and not declared? The return of check path is only assigned to the error variable. It doesn't create a new error variable. But where's the error variable then coming from? Where is it declared? VS Code actually knows this. If you right-click the error variable, find all references, then it will highlight all the uses of this variable and it shows all the outer ones. So here the variable is declared and everywhere here it's just used. The other variables that are declared and assigned are not highlighted. They are a different variable. You can also see that when you debug the Go code, we can set a breakpoint here and then investigate the variables dynamically. First, we see here the error variable, but let's single step forward until the next one. This one is declared. And now we can see that there are two error variables, one without parentheses and one with. If we look into the source code of the Go debugger interface in VS Code, you can see annotate shadowed variables in parentheses. So this is a so-called shadowed variable. Variable shadowing occurs when a variable declared within a certain scope has the same name as a variable declared in an outer scope. So if you debug the code, you can also see that something funky is going on with the variables here. And this is an issue. Remember, this code can run in parallel. So the error variable is accessed in parallel. And if you look closely, you can see that the check is done in two steps. First, the error variable is assigned and then it's checked. So what if the check path is called with flag.txt? It sets the error variable as expected, but then in parallel, another request sets the error back to nil. Then this check would pass, allowing you to read flag.txt. So that is what it was. It's a Go race condition. And I agree with the organizer's assessment that this is an easy challenge. Currency is fundamental to Go. If you are experienced with writing or reading Go, you probably should know this. But I didn't, and I'm very bad and inexperienced with Go. But thanks to the CTF challenge, I now am aware of this. And from now on out, when I read Go code, I will pay attention to the declaration and assignments, especially of error variables. Now, here is the final exploit code. It's super simple. We first get a session ID to initialize our personal key value store, and then we just spam requests to get a file that passes the check path function and writes nil into the error variable, while we also spam requests to read the flag.txt file. This will return an error, but if right afterwards the error is then reset to nil, it will leak the flag successfully. Now we can just run it, and depending on the networking and various other factors, eventually we will get the flag. By the way, this is also the answer to the question why this challenge has this unique and weird back and front end setup. If all CTF teams would share the backend binary or backend process, then everybody would accidentally race condition each other. By spawning a unique KV process for everybody based on the session ID, the race condition only happens within your unique session. Nobody influences each other. If you want to learn more about hacking, check out our online training platform hextree.io. We are still in early access, so there are still lots of content that we need to create, but I am still very proud of what we created so far. Also, Google sponsored our Android application security course. They have hundreds of apps in their bug bounty program, and they identified the lack of resources or good education as a major issue. That's why they contacted us. They hope that we can teach the next generation of Android application bug hunters. So give these courses a try. They were produced by Stack Smashing and me, and we did a lot of additional research to create them. This is not just knowledge that you can already find online. We also cover several vulnerabilities that we have found ourselves in various applications, and we created test applications where you can practice what you learned and hunt for flags. So come and check out our courses on hextree.io.